Thank you very much for the introduction and for organizing this very nice workshop and for giving the chance to be here. So first of all, is it big enough and loud enough? So if it gets not as loud and not as big, please let me know. Try to pick it up. Also, so I will discuss joint work with Mark Burger, Alexandra Yossi, and Anna. And last time I gave a talk about this topic in the fall, I said that this should appear on the archive next week, and I was not believing that myself. But indeed, it did appear on the archive in the last fall. So I'm very happy that I made it happen by an hour ago. So maybe I should tell this to be accepted next week. And also, I am not an algebraic geometer, and I'm speaking here about a topic coming from real algebraic geometry. So I will try to give you a bit of my motivation, the kind of question I'm interested in studying these topics. But please stop me at any point and ask me questions so that we are on the page. Okay, so what we are interested in are character varieties. So known by phi, gamma, g, where gamma is the finally generated group. And actually, a lot of what we do works with generality, but the group you should keep in mind that's most interesting for me and probably very interesting for you as well is the gamma a group of the given surface or curve of GFG. And instead, G would be a joint, very simple of an ensemble type. So the example that you should keep in mind here are, for example, P and QR, P, S, D, G, R, or Q. So these are the up to portioning by the center. These are the groups coming from linear algebra. And the character variety of space going to be the portion of the set of morphisms from gamma into G up to the G action level. So observe that semi-simple groups are semi-algebraic, real semi-algebraic, and in particular, this object here as a natural semi-algebraic structure. Real semi-algebraic. It means that can be defined by polynomial equality and inequalities in some affine space. And we will, in our work, we need an explicit one, an explicit model given by Jacob's moduli theory of universe.
It's at least the font size is about to get smaller.
And the main point is that, so if you think a little bit about these groups are non-compact. I start from non-compact groups. Then giving a homomorphism from a finally generated group is just giving elements in G that satisfy some polynomial equality that are given by the relationship of gamma. So this the homomorphism phase as an actual semi-algebraic structure as the group G has. And like these quotient is complicated because G is not compact. Taking the GAT quotient is not so straightforward, but can be done. in various ways. And I'm hiding under the rug all the which is totally theory that's important in what we actually do. And so this is the non-compact space, which I will try next to persuade you that is of geometric interest, that is from also from my viewpoint. And what we will do is to use, to study a standard compactification of semi-algebraic sets that comes from real algebraic geometry in this specific case, and understand the geometry of this. That's the plan of our work. And like discuss the perspective in but so like this real spectrum, so I'm not assuming that you know what the real spectrum compactification is, and I will tell you a little bit about what this compactification is in a little bit. Before I want to give you, I want to explain why from my viewpoint this is really the correct degree of generality in which I really want to study this. So I don't want to get complex, for example, but I really insist on having these real forms that makes some things more complicated. And then I will tell you a little bit about the general respective compactification and then our results about the specific respective compactification of this. So any questions on this or comments? Why? Why? So what I really want to think of, or need to think of today, is G, my semi-simple ligament. This is the geometry group of its geometric space. Where X is the quotient by G over the maximal compact sum. And it's a non-positive term. And what's important for us is that, like, for some example, in the case of ESL2R, this is really the other side of way. And in the case of ESP, one R, this is the single space that we've seen already today in Woodstock and yesterday in Rostock. And G acts on this space by isometry. And actually, what will play a role later is that X can be endowed with many different distance functions that are all equivalent but measured that with different time formats. So like there is, like you will see it in a little bit later, so this is right. But thinking of G as the isometry of X, let me think of the character variety as a kind of action gamma on these geometric space. And this is really the perspective I want to keep in mind. And I really, we would really want to understand some similar properties for the points that we understand points in the compactification geometrically is actually constant. And okay, so this works for any group, also the complex group, so it's a C or. But one reason why I really insist on the real perspective is that in this case, I get some interesting actions. So for me, I want to say a few words on China. Accurate theory here. So in the case gamma is the fundamental group of the surface, then there are connected components of the standard variety that only consist of phase positions that are incorporated. These are what are sometimes called Heidelberg. And so, and this is only true for some real G. There exist these surprising objects that are connected components of these character varieties that only consist of particularly nice actions, meaning that these actions like are faithful, so are come from injectable homomorphism and are properly discontinuous, which means that I can take the quotient and obtain and understand that these components as moduli spaces of locally symmetric. The base example of this is when you do this place at war, and then so being faithful and properly discontinuous means that the quotient of H2 modulo this action is a compact hyperbolic surface. So by imposition, the compact Riemann surface, and then this component is a semi-unified model for the time. G, which is the universal covering of the moduli space that we've seen.
So this is what we call each component.
Yeah, so that's like not say that in a second. So each components are the examples. So like this is a generalization of these each components. I'm gonna write this word in a second. Because but are there questions for this? So this two factor present fine. So that so this gives me a link. It's something that we've seen already in the here. And so this is particular, so like for me, I mean, as a geometric topologist, I really care about these nice actions. And the fact that they form connected components is nice because this gives some semi-algebraic structures on the moduli space. Like, it's always so that faithful properties for these actions are in closed subset of a character variety, but typically it's very badly inside the character variety. It's very fractal boundary and behaves very, very badly. But in this case, they form components, so they are as nice as the others. And also another, like maybe just saying it in words, another reason why it's very interesting to have connected components with this property is that because this gives a link to fixed bounded moduli spaces that we've seen yesterday in Vicky's talk. Because like as Vicky, so like there is going to be a much correspondence that links like analytic diffeomorphism between the character variety and the moduli space of fixed boundaries, where like reality conditions can be imposed on fixed bounded moduli space. Sign that tells you that you land in a group G, and these are still holomorphic data. So this like brings us in the world of algebraic geometry. And but in general, being connected component is something that I can see on the fixed bounded moduli space. Okay. And like you get your question about each component, we now fully understand what are these high rank activity theories. And then there's a theorem, combination of work of the fixed bundle moduli side from Raphael Collier. Okay, Goethe University. Plus, work on the characterizing viewpoint, by myself, with Jonas Weiler, with the guitar, also a brief dinner, which says that this hierarchical action theory are formed by so-called data point representation. And the sizing of the group is split. And here we're studying before and after each component. With our convolution type. And these were studied before and our maximum representations. Or for the group EO, EQ, that are new phenomena, and for the exceptional groups with group systems of data. And so what is what the content of this is that so we now fully this is so Tabular space is one of the most beautiful objects in mathematics. I think we all agree. It has its portions, and we have now examples of generalization of this for bigger groups where this action can be far from being compact. So it's more surprising that a component exists that only consists of geometrically nice representations. And we have a full classification of when this arises. In each of these classes of groups, there exists a number of hierarchical components with this property, and we can classify them all and understand the geometric feature behind this, which is some generalization of what happens in the vector space.
Well, what is theta positive?
Yeah, so theta positive is an algebraic motion that has it's the definition a geometric somehow the point is that if tell you what theta positive means, it comes from this Ishar-Wiener theory. And the point that for Lie groups in these classes, there exists a special flat manifold that corresponds to some set of single roots, which is theta, that has some partial civic ordering similar to this, that is the boundary of it. And using this theory, we can understand what the geometric reason behind these lines of the representation, and we have two ones, which is what we studied in the joint work here, which is not yet on the archive, but maybe we'll be
But it has nothing to do with the data stability of how to isolate. Not connected.
It is not connected. So this is really connected to one way of studying polymorphism of hyperpolarization is to look at maps from the circle. We can understand them at infinity. These actions are actions on the proper disk, but induce actions on the model. And this theta positivity is behind generalizing this feature for these other class functions. So this singles out explicitly a class of action of the surface, of implemented on the surface, that has a nice property, and we can show that it is for connected. More questions or comments? Okay, so and as you see, I have no complex would be here in this list, and so this for me is one motivation why I want to really look at this. generally the generality of the real right.
So in the case of split, is it not the teaching components? But
Right,
in
so
other cases, more general.
Exactly. So for split real group, for every split real group, there exists exactly one connected component, which is the connected component of the homomorphism coming from the useful embedding of PSL2R. That only consists of minus representation, this is the so-called Hitch representation, and this is the theta positive representation for theta, the full for theta, the full system. And in all the other cases, there is more than one component that we can understand. Most of these components contain some PSL2R embedding. There are some examples in here in POP+1 that only consist of the test. These components are nice being smooth. These are the only ones apart from the itching that are smooth as semi-algebraic variety. More questions or comments on this? Okay, so personally, I find these discriminating thing, and being semi-algebraic subset gives me a way of understanding the compactification if I understand the compactification of the whole factor. Like this. Okay, so few words about the respective compactification, which is the compactification you look at in general. So here I start from a real algebraic variety X. And I consider its coordinate rings with rational coefficients. Or I mean, I could do the same with the real, like a theory based on real coefficients, and will give slightly different quantifications. They R of X, so we get more points, I think maybe. Then real algebraic geometry constructs the topological space, which is the set of pairs where E is a prime ideal, and the order is the order of the fraction field, which extends the order. So this is a collection of points, and of course, not all for not all prime ideals in A, the fraction field will admit an order. Like for example, if this is starting from R, and this was the complex numbers, there is no order on the complex numbers that is set to C-squared. A lot of points in the spectrum, but I'm also making many points bigger. Typically, on R or on Q of X, there are lots of different orders that extend the order. Because I could say that X is bigger than any other number, or that 1 over X minus T is bigger than this gives me R value. Uncountably many different orders on the same. Right. So now, from my viewpoint, the nice thing of keeping track of these orders is that I can now put on this set a topology that extends the topology. That from a dramatic topological perspective is making the best better than the trace topology. Okay. Mark. That's and that's respecting the evaluation to the maximum price. And it's natural, we can just naturally define the constructible topology. The topology basically for any f in the base, for any polynomial or for every polynomial function or every rational function on x, it makes sense to say that f will be positive in because like after that gives me an element in ring for which I reorder in class is bigger or more than 0, which means it makes sense to consider sets of the form UF, so that these are the points were positive is a nice subset of F that gives me a basis of the topology that extends the deep topology. So basically, looking at this real algebraic construction that like keeps that for which it is important that my base field is not algebraically closed, let me talk about open set and let me talk about semi-algebraic. And let me construct semi-algebraic subset in this real spectrum compactification. It will be the constructible subsets that are extensions in this set of the semi-algebraic subset. And now there are two surprising properties. So we'll consider the real spectrum together with this topology, this constructible topology. And so there are this topology is not separated. Not every that's but every point has a unique closed point in its group. So like and not every point in this real spectrum is closed, there is like almost there is topology, but here we have this strong property that for any point there is this unique closed point level. Which means that we can consider continuous refraction from the full real spectrum to the closed point. The continuous. For the differential geometry, I don't really like having to deal with all those points, but in this case, I have this nice curve that this subset is a product of the whole space. So I can just consider this set of points. And close. Gives me a natural compactification of my dimensional set that comes from in some sort of like algebraic algebraic construction, but still with a twist given by the order. It is not that I want to have it's all well-known things, but we will want to look at specify this through the case of character varieties and try to understand properties of them. Any questions or comments on this? Okay. So like maybe the first theorem that we prove is like a characterization of points in this real spectrum compactification, an interpretation of points in this real spectrum compactification of character varieties. We understand this as that of suitable complexity classes or representations from gamma to G of F. One where F is real close. General real up to suitable. The suitable relations that are given by these isomorphisms and so what does it tell me? This tells me that like in the case of character variety, that were understood as some portion by the G-axial conjugation of homomorphisms into my real liquid. I can understand points and with real algebraic compactification coming from real algebraic geometry in terms still of actions, still of homomorphisms, but now in some more complicated groups, which are so G would take algebraic groups, so I can consider it over other fields that are not R. And here I consider virtual fields, which are like make the nice. And these are being here close means that F is ordered and it's maximal among that has no algebraic extension to which to order. So this is the same, like R is not algebraically close, but it's real close, meaning that it's as big that it has no algebraic extension to which to order. This will always be an order to subfield of it algebraic. But as I was, so this real spectrum here is still a compact space if you're not French, so it's not separated, but it's still compact. And but I like much rather work with this separated space, that's a subset of those. And so the first big thing that we prove is the understanding when giving a characterization of those points among those actions. Which of these actions give rise, which is what I sort of
We are all the time on considering on the reductive representations, right? Because we want to work with the reductive.
Right, yeah, so like I can, yeah, like I'm plotting on the graph of like of this conjugation that is not so, that like I can think of this just as reductive representation or extend the notion of conjugation to make it like more reductive representation, the same as this. Yeah, thanks. Any more questions for this? And like, you know, this first result is not really very hard, but in order to get such result, we need a good model of the GAT quotient, that's MS right. And like somehow we need to turn Richardson's moduli theory gives a model for the GAT quotient, like the quotient by conjugation, like the compact proof, which is not semi-algebraic in nature, and then turn this into a semi-algebraic description of all the options involved, so that we can check the GAT quotient is well at the level of factor right. Such a result can interpret points in compactification as well as interpret the same. Well, so what telling you that I want to think about the real point, the actual point of the character variety, as action from semantic system. And similarly, in order to give a characterization of close points, we want to think about these homomorphisms into this group with like big coefficient, like the field you should keep in mind there is R of X, I mean the real closure of R of X. So some like biggest algebraic extension of R of X, one up to R of X. And in terms of action on some nice metric space that is some analog of symmetric. And now here we use the fact that if I consider that I get back to the symmetric space, then this also is a semi-algebraic set. So this is what was like appearing in the end of the most scope of this minimal structure on the units. So this is natural structure. And can be defined as a semi-algebraic set. I have explicit models of this as semi-algebraic set. So in particular, I might consider with F points. So this is like, for example, in the half plane, we can say the example very good. So we all know that the model for the concurrent disk are complex number with positive imaginary part, but say, these make sense also over F. It's two F compares X with Y or Y greater than 0, which makes sense because all the systems considering are ordered. So talking about the positive point makes sense. So I can consider this set, and the action of G on X is semi-algebraic, which means that this is as a natural G action, and can be identified as G of F In particular, if I think of these as suitable equivalence classical actions of finite generated groups, of homomorphism for finite generated groups into geometry, these objects act on this symmetric space over F. And something that we prove is that any invariant distance on X, this is what I was alluding to before, that X, the symmetric space has lots of G of R invariant distances, and these come from the bigroup invariant norm on the maximal flat. Like for any, there exists a unique, so any G invariant distance on X uses a multiplicative variance on X. So for any real closed field, so for any G invariant distance on X, and for any F real closed, there exists multiplicative F value distance on F that extends this distance. And all these distances are equivalent. And the metric portion of D composed with D is this. Right. So, okay, so like basically what we do here is that so on the hyperbolic plane, we have over the reals, we have the standard distance, which is the log of the cross vector. This, like in hyperbolic geometry, the distance between 2 points is I take the geodesic and I take the log of the cross ratio between these points, and the cross ratio gives the multiplicative distance on the hyperbolic. And this is a very general story that works for all symmetric spaces. And so we get lots of pairwise equivalent multiplicative distances, that is X of a distance, that is F value, as values in this real closed field. But I like to take or to think about spaces and to think about classical metric spaces. I consider I consider the one way like this. There is an analog in this setting of real closed field. There is evaluation, which plays really in this setting the role of a logarithm, which is not a homomorphism anymore from the multiplicative group to the additive group. It's like has a big kernel, but still I can use to turn a multiplicative distance that has values in F, bigger than 1, to an additive real value single distance. And this leads us to consider the metric portion for V of F is from the metric space on which V of F Basically, what I've done here is that I've done some generalization of classical hyperbolic geometry for symmetric spaces to obtain from some F version of the symmetric space a metric space on which my groups that arise in my respective compactification of factor variety act by them. So now I can think about this point in the respective compactification as action of gamma on these metrics. Mark that for rho thesis for SLR, SLN, and F the Robinson group shows that the V of F is the Goethe building. Of so this metric space is a Goethe building. In general, the thing is more delicate because for the fields that we really take, that we really appear naturally, this valuation is not going to be subjective. So you need to do some apartment competition to get back the Goethe. But there are strong links between these metric spaces that we geometrically construct, starting from symmetric spaces, and Goethe's building of these groups with values that we take. So. Questions on this? Okay, then I can tell you our factorization. Is that the point in the real factorization of the factor variety is good point. The action on the is fixed. This is something that I really want. Like geometrically, is a very nice property that is an analogy with like the study of action. And the idea is that in factor varieties, it's not always so that the action in the symmetric space is 6.3, but if the action of the symmetric space is a global fixed point, then this is contained in the factor variety we value the maximum compact group. And so it's like it's already compact, so there is no need to compact. Yeah.
Can you comment on how that relates to first compactification with compactification?
Right. So that's so this is maybe that's what I was gonna say in maybe the last 10 minutes. So, but in a sense, these compactification, like this is what I'm gonna like. Let me just give you.
Yeah, let's just okay, just go on.
Yeah. Let me get there. Let me pause on this 1 second while I mess up the words shifting. And let me actually answer, like finish my talk by answering Martin's question on the relation with the Tarskis compactification. Okay. In the PSL2 case, and maybe linking with some other things, so that the short answer is that this is bigger. This is bigger, this compactification, this and dominate. So like maybe let me just say a few words to motivate what I'm gonna do next. So like in rectangular space, Tarston compactifies the rectangular space through action complete. And this is very similar to what is happening. Because here we are compactifying the rectangular space in the case of the component of the PSL2 character variety with actions on these spaces, and these spaces are gonna be tricky, or like we can complete them to be tricky. But what we keep track here is really the algebraic nature of this tree. Because it's a, like out the duality building that appears in this setting, if I do this compactification in SL2R, comes together with an SL2F action. And I'm still remembering this representation as a defect. And this gives me some, like, this says that there will be a map, which would be forgetting this algebraic nature of my field, forgetting the big G action of just remembering the gamma action on this tree, but making several deductions equivalent, which gives me like the projection from this space to the partial compactification. But something, for example, is nice setting is that if I go to infinity Wagner space by twisting or pinching, these I will be able to see as different ones in this compactification. So there will still be a color, but this will be of different nature. And I can see through this, through remembering more of the, like, if you want the most standard hyperbolic geometry underlying it.
So does it arise with blowing up some boundary strata, or what is?
Yes, that's a very good question. I cannot, I don't know. I expect so. I expect that in the Tasman case, over like laminations is a one-to-one thing, and like other boundary strata gets blown up through different valuations, but I never really imagined it.
Along that line, like this seems like it should be really big. Does this compactification kind of dominate any other one that you?
Right. So this compactification should dominate any other natural algebraic compactifications, and this is the case for lots of things that we have been discussing. So there are some compactifications in this business that come from truly analytic techniques and that are really non-semi-algebraic in nature. Those like are a bit orthogonal to this story, but they dominate many. And some power of this to the domination results that we discussed in second, one example of these domination results is that these real spectrum have very nice properties. Very nice, for example, algebraic topological properties or path connected carbon accessibility and infinity properties, which we can then import on other compactifications that are less related topological. Or comments or questions? Now let me write a few things to like generalize this thing that I didn't word about the relation with compactification in a slightly different way.
I have a question. I'm a bit confused when you say what is building. Is it really the full building or the versus building?
Right. So the point is that if in the Robinson field case, the valuation is projected. So everything is first. Okay. So that's why that's the regular. For the like small field that actually play a role in this discussion, I will only get this countable set of like countable connection of vertices. And that's why their relation with Goethe building is complicated. Because I would need to get the Goethe building, I would need to do an apartment condition. But it's not the metric condition. So like for these fields here, you do the metric condition with respect to the metric, you complete all the apartments, you get the apartment, but you get extra terminal vertices. Like the Goethe building is not magically complete in the natural. So we never wrote this down because like the relationship of buildings is complicated enough, and you would have 100 pages for 150 pages paper, but the picture is pretty good. They are cut zero, like they're so the amount they're not cut zero because they're not complete. Because like typically my field is highest possibility, which means that I get only some sort of random in R. Like my valuation is gonna be onto some Q or something like that. As part number field over subset of R. So this gives a problem. But as a medium property, if you take like, as I was writing here, I have lots of different metrics, among which I can put the zero metric. And if I put the zero metric, it has the medium property, which means that the zero completion is the zero space. And it's going to have terminal vertices and like. So I'm not sure. Yeah.
Yeah, so we're in theorem. So then the space of these fixed point reactions has to be compact.
Right.
Is that clear a priori or is that only a posteriori?
No, I think it's a posteriori.
And that,
So like how I wanted that. So for me, the power of this respective compactification is that it arranges modular suitable equivalence relation all these fixed point reactions into a number. So somehow, like maybe I will not tell you about the compactification more than what I said already. That's probably finish here. But right, so like now Parot studied compactifications of these character varieties with actions in physics. And so, but this is a Mark-length spectrum kind of compactification. Maybe doesn't just write this. Another more naive way of compactifying this is to consider that the inductive length from the character variety so this is another way of realizing the class of compactification we discussed before. And this is what Annie proved in her thesis is that so what I do here is that I'm thinking of the character variety as actions on building on spectrum space. And this map here associates to an element gamma the length so that the infinity with the x in the United space or the distance with the x. So this is a translation like I pick one metric on the symmetric space, and I look at this space translation. This gives me a way of mapping the character variety into some infinite dimensional projective space. And Parot proved that this is a compact closure. And this gives a way of compactifying. So like for relativity, it's true that this embedded this map, this continuous map on the character variety to projective space, as compact closure can be used to compactify, and also she proved that every limiting like function arises from action on building. But now counting the respect to compactification if it is visible, then we will have what we took the theorem that I'm not able to say for reason of time, is that this real spectrum compactification dominates these compactifications, a continuous projection on the compactification. And but in particular, that compactification arranges all these actions on buildings in a compact matrix, which is otherwise not clear how to really arrange this in a compact. And I wanted to mention a little bit, link back to hierarchical theories, and say that in rank 2, there is an interesting link with cone surfaces, but maybe a later.